Let's look at the ion product constant of water, Kw, which is defined as the equilibrium constant for the auto ionization of water. Okay, so the equation for the auto ionization of water is H2O forms hydrozonium ion plus hydroxide ion. Then you balance the equation. Then the equilibrium expression is given by K is equal to concentration of hydrozonium ion times concentration of hydroxide ion over concentration of water squared. So this is the equilibrium expression. Okay, so since the concentration of liquid water is essentially constant, this is the concentration about 55.5 molar. Okay, so when this is incorporated into the equilibrium expression, since the concentration of water is a constant, so this now becomes Kw. Hydrozonium just the same as hydrogen ion. Okay, so it will be Kw is equal to hydrogen ion concentration times the hydroxide ion concentration. Okay, so where Kw is ion product constant, then this is hydrogen ion concentration, then this is hydroxide ion concentration. Okay, so at 25 degrees Celsius, at 25 degrees Celsius, the value of Kw, so at 25 degrees Celsius, Kw is equal to that, which is equal to 1.0 times 10 to the power negative 14. Okay, so that is the value of Kw at this temperature, at 25 degrees temperature. So Kw is affected by temperature. Okay, so let's quickly look at the effect of temperature on Kw. Effect of temperature on Kw. Okay, so the value of Kw changes with temperature because the ionization of water is an endothermic process. Okay, so ionization of water is an endothermic process. Ionization of water is an endothermic process. So we know it absorbs the heat energy. Okay, so increasing temperature increases the extent of ionization. Okay, so increasing temperature increases the extent of ionization. Okay, so let's have some values. We see how temperature affects Kw values. Okay, so we shall start from 0 degrees all the way up to somewhere 100. Okay, so temperature, then kW. Okay, so at 0 degrees kW, it's somewhere 0.114 times 10 to the power negative 14. Then at about 10, it's 0.23 0.293 times 10 to the power negative 14. Then at 20 it goes to about 0.681. These all of them, it's times 10 to the power negative 14. Okay, then at 25 degrees Celsius, it's 0.008 times 10 to the power negative 14. At 30 1.471, then 40 2.916, then 50 5.476, all the way up to 100, and then at 100 is somewhere 51.30. Okay, so these are the Ka values. As you can see, as the temperature increases, the kW, these are the kW values. So as temperature increases, kW also increases. The reason being, the process is endothermic. Okay, the auto-ionization of water is endothermic process. Okay, so now let's look at the concentration of hydrogen ion and hydroxide ion in pure water. Okay, so for pure water at 25 degrees Celsius, for pure water at 25 degrees Celsius, we know that Kw is equal to hydrogen ion, OH, which is equal to 1.0 times 10 to the power negative 14. That is at 25 degrees Celsius. Okay, so pure water has equal concentrations of both ions. Okay, so the concentration of hydrogen ion is equal to the concentration of hydroxide ion. Okay, that is for pure water, which is equal to X. Okay, so we can solve for X. Okay, so in this case it will be X squared is equal to 1.0 times 10 to the power negative 14. Okay, so X will equal to the square root of this, which will give us 1.0 times 10 to the power negative 7. Okay, so X, which is equal to that, so it means for pure water the concentration of hydrogen ion is equal to that. Then also the concentration of hydroxide ion is equal to 1.0 times 10 to the power negative 7 molar. That is at 25 degrees Celsius. Okay, then We can also look at the pH scale, the pH scale, okay. So the pH scale is used to express, so this express the acidity and basicity, acidity and the basicity of a solution, okay. So we know that pH is equal to negative log hydrogen ion concentration, then POH is equal to negative log hydroxide ion concentration, okay. Then now, what's the relationship between pH, relationship between pH and POH, relationship between pH and POH, okay. So at 25 degrees Celsius, pH plus POH is equal to 14.00, okay. So that's the relationship. So we can calculate the pH of pure water at 25, okay. So we know that pH is equal to negative log hydrogen ion concentration, so it will be negative log, since at 25 we have this, okay. So it means pH is equal to 7 of pure water at 25. Then POH will equal to 14 minus 7, which will also give us 7, okay. That's the pH. So what this means, when we are looking at the pH scale, we know that numbers less than 7 are for acid, greater than 7, then greater than 7 for base or alkaline, then exactly 7, that is neutral, okay. So for acid, hydrogen ion concentration is greater than hydroxide ion concentration, so in this case pH will be less than 7. Then neutral, hydrogen ion will equal to hydroxide ion, which is hydroxide ion. So in this case pH will equal to 7. Then for alkaline, hydrogen ion will less than hydroxide ion, so pH will be greater than 7, okay. So now, what is the effect of temperature on neutral pH? Effect of temperature on neutral pH. How does the temperature affect neutral pH? Okay, so since Kw changes with temperature, neutral pH also changes, okay. Since Kw changes with the temperature, neutral pH also changes. Neutral pH also changes, okay. So as we can see, from the table that we're about to draw, so let's see how the temperature affects neutral pH. So temperature, then we know that Kw, we have done that already, Kw as temperature, so we are not going to include the the part for KW. So let's just look at pH and pOH. We already know the effect of temperature on KW. It increases as the temperature increase. So at 0 degrees Celsius, the pH of pure water somewhere 7.4, 7.47. Okay, then at 10, 7.27, 7.27. Then 20, it goes to 7.08, 7.08, 7.08. Then 25 is the one that we know, 7.00, 7.00. Then 30, at 30, it goes to 6.92, 6.92. Then 40, it goes to 6.77, 6.77. Okay, then lastly 50, it goes to 6.63. Okay, so here you can see clearly that as the temperature increases, the pH goes down. Okay, it reduces. You can see at 0 it is 7.47. Then as it reaches 50, then it goes to 6. Okay, it decreases. As the temperature increases, pH decreases. Then the one that we know is this one we are used to at 25. Okay, which is a pH of 7, neutral. Okay, so now there's an important point that you need to consider. Okay, so even if the pH is not equal to 7, the solution is still neutral. The solution is still neutral, provided hydrogen ion concentration is equal to hydroxide ion concentration. So this is what defines the neutrality. Okay, so it doesn't necessarily mean that the pH has to be 7 for it to be called neutral. So when we look at these other solutions here, the pH, you can see at 0 it is 4.7, 7.47, 7.47. This is a neutral solution. At 20, 7.08, 7.08. They are equal. It's neutral. Okay, so as long as the concentration of hydrogen ion is equal to the concentration of hydroxide ion, that defines neutrality. Okay, so we can write these points. Okay, so neutral condition means hydrogen ion equal to hydroxide ion. That's a neutral condition. Okay, then neutral pH decreases with the increase in temperature. Okay, so as temperature increases, neutral pH decreases. Then also always check the temperature when interpreting pH. Okay, always check temperature when interpreting pH. As we can see, temperature affects pH. Okay, then also do not always assume, do not always assume pH of 7. Do not always assume neutral. Do not always assume neutral as is equal to pH equal to 7. Okay, do not always assume neutral pH is equal to 7 unless it's at 25. Unless it's at 25 degrees Celsius. Okay, so that's a condition. So pH equal to 7, it means the temperature is at 25 degrees Celsius. Okay, so let's look at weak acid and weak bases. Weak acid and weak bases. Weak acids and weak bases. A weak base B partially dissociates. So a weak base, so let's start with weak acid. Weak acid, not base. We follow the order. Weak acid, HA. Let's start with weak acid, HA. Okay, so a weak acid, HA, partially dissociates in solution. So the reaction is reversible. So weak acid will dissociate to form hydrogen ion plus the conjugate base. Okay, so how can we calculate the pH of a weak acid? So we use the approximation method. Okay, so for this approximation method, we are going to compare the values of concentration of the acid over the concentration over Ka. Okay, so we are going to say concentration of acid over Ka value. If it is greater than or equal to 100, it means approximation is valid. Okay, that is if it is greater than or equal to 100. Okay, so if it is valid, so it means the concentration of hydrogen ion is equal to root Ka times the concentration of the acid, like that. Okay, that is how we can calculate the concentration of hydrogen ion. Okay, then from there now we know pH will equal to negative log hydrogen ion. That is pH. Okay, then in next we can also calculate OH. OH, we know OH can be calculated from Kw. Okay, Kw over hydrogen concentration. You know this equation. Okay, then also we can calculate POH. Okay, POH will equal to 14 minus pH. That is POH. Then we can also calculate percent ionization, which is equal to concentration of hydrogen ion over concentration of the acid times 100. Okay, so having done this, we can now calculate the pH. So let's have an example. Let's see how we can calculate the pH of a weak acid. Okay, so we calculate now the pH of a weak acid. Let's calculate the pH of a weak acid. Okay. The question is calculate pH. Calculate pH. Calculate pH. pOH. Hydroxide ion concentration. Hydrogen ion concentration. Hydrogen ion concentration OH. And percent ionization of 0.10 molar acetic acid. Okay, 0.01 molar acetic acid. So this is acetic acid. Okay, so let's calculate the pH of this acid. 0.10 molar. Okay, so solution. So first of all, we need to check if we can use if the approximation method is valid or not valid. Okay, so we are going to apply our approximation method. So concentration of the acid over Ka. So concentration of the acid 0.1 over Ka. Ka for acetic acid is equal to 1.8 times 10 to the power -5. Okay, so that is the Ka for acetic acid. So we bring it here, -5. So we divide that. When we divide, we are getting 5556. Okay, so you can see this number is greater than 100. It's greater than 100. So it means approximation is valid. Approximation is valid. Okay, so if it is valid, now we apply the formula. Hydrogen ion concentration is equal to root Ka times concentration of the acid, since it is valid. So which is equal to 1.88 times 10 to the power -5 times 0.10. Okay, so you multiply and find the square root of that. Okay, so it will give us 1.34 times 10 to the power -3 molar. Okay, so this is the concentration of hydrogen ion. Okay, so now since we know the concentration of hydrogen ion, we can calculate the pH. So pH is equal to -log hydrogen ion concentration, that is pH. So which is equal to -log 1.34 times 10 to the power -3, which will give us 2.87. So 2.87, that's the pH. So if we know the pH, we know the OH. Okay, so we can also calculate OH. concentration. Okay, so we know OH is equal to Kw over concentration of hydrogen, 1.34 times 10 to the power negative 3. So concentration of OH, so we divide that number, it will give us 7.46 times 10 to the power negative 12 molar. Okay, so that is the concentration of hydroxide ion. Then what else do we need? We need also, from the question, we need also POH. Okay, so POH will equal to 14 minus pH, 2.87, which will give us so we subtract that. Okay, so it will give us 11.12. so 11.12, that is our POH. Then now we need to calculate the percent ionization. Okay, so percent ionization will equal to the concentration of hydrogen, which we have here, 1.34 times 10 to the power negative 3 over concentration of the acid, concentration of the acid, which is 0. It's here 0.10 times 100%. Okay, so we divide and multiply. So we're going to find that it is 1.34. Okay, so you can see here that the percent ionization is less than 5%. Remember the 5% rule. Okay, so if it is less than 5, then we neglect X. If it is greater, then we use a quadratic equation. Okay, so let's have another example. We see when the percent ionization is greater than 5%. It's greater than 5%. Then in such a case, we need to apply the quadratic equation. So calculate the pH. Calculate the pH of chloroacetic acid. Chloroacetic acid, which has a formula ClCl2COOH. That is chloroacetic acid. Okay, so we can just abbreviate it as HA with the of concentration. So the concentration is 0.01 molar. Ka for chloroacetic acid. Chloroacetic acid is 1.4 times 10 to the power negative 3. Okay, so calculate pH of chloroacetic acid, 0.01 molar. Ka 1.4 exponent negative 3. Solution. Okay, so the first thing to do is to check concentration of acid over Ka. Okay, so concentration of acid in this case is 0.01, Ka 1.4 times 10 to the power negative 3. So now we divide this number. It is giving us 7.1. So 7.1 is less than 100. So it means approximation is invalid. Approximation is invalid. So we cannot use the hydrogen ion concentration is equal to root Ka. Ka times the concentration of the acid. So now we need to apply quadratic. quadratic equation. Okay, x is equal to negative b positive negative root b squared minus 4ac over 2a. Okay, so this is a quadratic equation which you know. Okay, so now we need to apply quadratic equation. So we need to write the we need to come up with the ICE table. Okay, since the approximation is invalid, come up with ICE table. So let's write the ICE table. Let's dissociate the chloroacetic acid, CH2COH. So this one will form hydrogen ion plus okay, so we're going to have this. So ICE. Okay, so the concentration of the acid is 0.0100 minus x plus x plus x. Okay, equilibrium 0.01 minus x x. Okay, then now we write the Ka is equal to 1.4 times 10 to the power negative 3, which is equal to, we know Ka it will be hydrogen ion concentration times ClCH2COO, then over acid. Okay, then now we substitute the equilibrium concentrations. So it will be now 1.4 times 10 to the power negative 3, x, hydrogen ion is x, this one is also x, so it will go to x squared over, for the acid, 0.01 minus x. Okay, then now you cross multiply to create a quadratic equation. Okay, so that is a mathematical situation which is very simple for you. Okay, so you cross multiply, then now you form quadratic equation. Form a quadratic equation. Okay, so when you form a quadratic equation, you are going to find your x to be 0.0000311. Okay, so that is the value for x. Of course, quadratic will give you two values, negative and the positive, so only consider the positive value. Okay, so this value of x, that is now the concentration for hydrogen. Okay, so hydrogen ion concentration is equal to 0.0000311 molar. Okay, then now we can calculate the pH. We can now calculate the pH. So the pH will be negative log that. Okay, so pH will be equal to negative log 0.00311, which will now give us the pH. pH will be equal to 11 point no, the pH. So let's calculate the pH. 2.51. It cannot be 11. 11 is for us, for bases. Okay, so the hydrogen ion concentration is this, then the pH is 2.51, which is making sense since it's an acid. Okay, so if we know the pH, we can also calculate POH. You know how to do that. Then now let's check the percent ionization. Let's check the percent ionization. Let's check the percent ionization. So percent ionization or dissociation is just one and the same. So percent ionization is equal to hydrogen ion concentration over concentration of the acid times 100%. So hydrogen ion concentration is equal to 0.01. Okay, I mean hydrogen ionic concentration, the one that that we found, which is 3.11 times 10 to the power negative 3, or 0.00311. Then the concentration of the acid is given 0.01 times 100. Okay, so when you do your calculations here, you are going to find it is 31.1%. So you can see it is greater than 5%. So here the 5% rule does not apply. Okay, so let's quickly look at also the weak base. The weak base. Okay, so the weak base accepts a proton. A weak base accepts a proton. A weak base accepts a proton. So base plus water will give us this, plus hydroxide ion. Okay, so approximation method, like the one we have done for an acid. Okay, so hydroxide ion concentration is equal to root Kb times the concentration of the base. Okay, then pH. So normally we know when to apply this. It means concentration of the base over Kb is greater than or equal to 100. That's when that will apply. Okay, so concentration of the base over Kb should be greater than or equal to 100. Then pOH is equal to negative log hydroxide ion. That is pOH. Then pH is equal to 14 minus pOH. So we can also calculate percent ionization, which is equal to concentration of OH over concentration of the base times 100. Okay, that is for concentration of the base, Cb. Okay, so let's have an example. Let's see how we can calculate. Okay, so example, calculate pH. Calculate pH of ammonia. Calculate pH of ammonia with concentration 0.15 molar. Then Kb for ammonia is 1.8 times 10 to the power negative 5. Okay, calculate pH of ammonia 0.15 molar. Okay, Kb is equal to that. Okay, so solution, let's check for our approximation method. Okay, so check Cb over Kb, okay, which is equal to Concentration of the base is 0.15 molar. Concentration, Kb 1.8 times 10 to the power negative 5. So it is giving us, divide that number, we are going to get 833, which is greater than 100. Greater than 100. So approximation is valid. Approximation is valid. So if it is valid now, we can straight away calculate OH concentration. So OH concentration is equal to root Kb then Cb, which is equal to Kb 1.8 times 10 to the power negative 5 times Cb 0.15. Okay, so we find the square root of that, which is going to give us 1.6 times 10 to the power negative 3 molar. So this is our OH concentration, hydroxide ion concentration. Then POH will equal to the negative log of that, okay, negative log 6.4 negative 3, which is equal to 2.78. that is POH. Then pH we know it is 14 minus 2.78, which is giving us 11.22. Then we can also calculate the percent ionization, which is equal to the concentration of the base, concentration of hydroxide ion, over Cb times 100. Okay, so concentration of hydroxide ion, which is 1.64 times 10 to the power negative 3, base 0.15 times 100. So we divide and multiply, which comes to 1.09%. Okay, that is the percent ionization. So you can see it is less than 5%. It is less than 5%. And remember, when we are looking at those ICE tables, when it is less than 5%, we neglect X. Okay. Then for situations whereby if concentration of the base over Kb is less than 100, then apply quadratic equation. Okay, so that you can do the way we have done it for an acid. You apply quadratic equation, meaning you are going to form an ICE table. Then now you form a quadratic equation, and so for X, that will be the concentration of hydroxide ion, the way we did it for acid. Okay, so thank you. We can end here. The next lecture will be on salt hydrolysis. We want to see how we can calculate the pH of a salt. Okay, thank you.